Yes.
So today we'll be teaching on logarithm. Now, what this place is trying to say, so logarithms can be expressed in other bases apart from base 10. So when we are talking of logarithm, we are not just talking of base 10, like in the standard form. So in logarithm, any other base can come to play: base 1, base 2, base 3, base 4, base 5, on and on. The logarithm of a number to a given base is the index or power to which the base must be raised so that it is equal to that number. What this story is saying is simply this: said the logarithm of a number to a given base. For instance, this is log n, and this is the base, which is b. This is the base here, and n. Okay, let me write it out. Where b is the base, n is the number, and x is our index or power. What this place is trying to say is that the logarithm of a number to a given base, this is log n base b, log n base b. Now the logarithm of n to the base of b is the index or power to which the base must be raised. We are trying to compare indices and logarithm here. That is what this sentence is about. So the logarithm of n to the base b is the index. When you write this out, n, b, and x, when you write it out in indices form, we have n is equal to b raised to power x. So we are saying the logarithm of a number, which is n, is the base. The base remains constant. We know that in logarithm, b is our base, x is our what? Index, n is the number. So b remains the base in indices and in logarithm, but your power and your number is interchanged. That's just the difference between indices and logarithm. So the logarithm of n to the base of b is the index of that number, is the index of n, the index which is x. So if we are given log n base b is equal to x, you can express this in index form. That is what this sentence is trying to tell us. So we have that the form n is equal to b raised to power x is the index form. That is the index form of writing this expression. While the form log n base b is equal to x is the logarithmic form. So that is for every logarithmic equation or a logarithmic expression, there's the index form. So for example, if we have 1 log 8 base 2 is equals to 3, it can also be written as 2 raised to power 3 is equal to 8. Don't forget our base remains the same, while the index and the numbers are interchanged. So log 8 base 2 is equal to 3, while it is the same thing as saying 2 raised to power 3 is equal to 8. The second one, if we have log 1000 base 10 is equal to 3. It's the same thing as saying 10 raised to power 3 is equal to 1000. Okay, so I clear the board. The third example, we have log 8 base 2 is equal to 3 over 2. It's the same thing as saying 2 raised to power 3 over 2 is equal to square root of 8. And we also have log 1 over 32 base 2 is equal to minus 5. It's the same thing as saying 2 raised to power minus 5 is equal to 1 over 32. And 1 over 32 is the same thing as 1 over 2 raised to power 5. And we apply our, what's it called? Negative indices. We have this. So that is that for logarithmic expression and index expression. Now we'll move a step further. If we are given how to solve equations relating to logarithm, now we are given equations and we are asked to solve. So the first example we'll be considering, if log 81 base 3 is equal to p, we are asked to find p. We are given logarithm of 81 base 3 is equal to P. We are asked to find P. How do we go about this? Having showed us the relationship between indices and logarithm, we apply that relationship here. If we have log 81 base 3 is equal to P. Log 81 base 3 is equal to P. In index form, is the same thing as saying 3 raised to power P is equal to 81. Now we solve this equation further. We already dealt with this when we spoke about, I think, exponential equations in indices. When you have something like this in indices and you have your number, we have to break down the number into a base and an index that has a relationship with this side. You are breaking down your right-hand side into a base and an index that have a relationship with the left-hand side. So we have 3 raised to power P is equals to 81. 81 is the same thing as 3 raised to power 4. When we say 3 in 4 places, 3 times 3 times 3 times 3, 9 times 9, 81. So 81 is the same thing as 3 raised to power 4. So if 81 is the same thing as 3 raised to power 4, that means 3 raised to power P is equal to 3 raised to power 4. And here we said we equate indices, equating indices or equal bases. Since the bases are equal, they cancel each other out. That is the ideal thing. So we have what left? P is equal to 4. So that is the answer for our P. So the second example, if okay. If log square root of 8 base 2 is equal to x, we are asked to find x. So clean the board. Finding x here, when we represent log root 8 base 2 is equal to x in index form, is the same thing as 2 raised to power x is equal to square root of 8. Now, square root of 8, square root means the power of half. In mathematics, when you see square root, it means the power of half. So this means 8 raised to power half. Half is the same thing as square root. Square root is the opposite of square. So if square is raised to power 2, square root will be 1 over 2. So we have 2 raised to power x is equal to 8 raised to power 1 over 2. Now don't forget that we are to break down our right-hand side into a base and index, or base and power that has a relationship with the left-hand side. So how does 8 raised to power half relate to 2? 8 is the same thing as 2 raised to power 3. 2 in 3 places, 2 times 2 times 2 will give us 8. So we have 2 raised to power x is equal to 2 raised to power 3 into bracket half. Our power of half is still there. So when we open bracket, we have right here 2 raised to power x is equal to 2 raised to power 3 times half.
Sorry, please excuse me.
2 raised to the power x is equal to 2 raised to the power 3 over 2. When we equate indices, or we say equal bases, we have 2 raised by x is equal to 2 raised to the power 3 over 2. 2 cancel 2. So we have x is equal to 3 over 2. That's the solution for that. 3, if we have 1 over 2 raised to the power m is equal to 8. How do we go about this? Find m. So if we write out these indices in logarithmic form, we have 1 over 2 raised to the power of m is equal to 8 is log 8 base 1 over 2 is equal to m. Don't forget that we interchange the power and the number. The base remains the same. So we have log 8 base 1 over 2 equals to m. This is simply your answer. Then I hope I'm not too fast with cleaning the board. Okay. So if we're also giving question 4, log 0.0625 base 4. Now log 0. We have to solve the 0.0625 base 4 is the same thing as saying, okay, we don't have our number. So we say, in this case, we say let log 0.0625 base 4 is equal to x. So we are making an assumption now. So let's say the answer we are looking for is x. So because we are looking for the answer to this alphabet to find. So we are just assuming that what we are looking for, our answer is x. So having this, we can represent in index form. So when we represent in index form, we have 4 raised to the power x is equal to 0.0625. Now we can say that we want to represent the right-hand side in a base and power that has a relationship with the left-hand side. But yeah, we are dealing with decimal number. So we have to represent this as a fraction because we are dealing with decimal number. So it will not be easy to solve like that, finding the index or whatever of a decimal number. So we have to represent this in fractional form. So 0.0625 is the same thing as, so we have 4 raised by x is equal to 0.0625 is the same thing as 625 over. Now, how do we know that it is the same thing as over 625 over 10,000? You just simply count the numbers after your decimal point. The numbers after your decimal point tells you, how should I put it now, how many zeros you are dealing with. Now we have 4 digits after our decimal point, 1, 2, 3, 4. So that means we are dealing with 4 zeros. That's how we know it is 10,000. If it is 0.625, we are dealing with 3 digits after the decimal point. That means this is 625 over 1,000 because it has 3 digits. Don't forget that 1,000 has 3 zeros. 10,000 has 4 zeros. So the number after the decimal point tells us how many zeros we are dealing with. So we have 0.0625. 4 digits after the decimal point, 1, 2, 3, 4. So we know we are dealing with 10,000. So 4 raised by x is equal to 625 over 10,000. It's the same thing as 0.0625. So let's break down 6 to 5 and 10,000 into basis and index, or we reduce to its lowest form. Either way, we have 4 raised to power x is equal to, if we say we should start reducing this, 625 is the same thing as, now let me do with 625 over 1,000 first. Sorry, over 10,000. 625 is the same thing as 25 times 25. 10,000 is the same thing as 100 times 100. Now, if we break down 25 times 25, 25 times 25 is the same thing as 5 times 5 times 5 times 5. And 100 times 100 is the same thing as 10 times 10. This is 100. This is 25. This is 25. So let's say we are doing it this way. So 100 is the same thing as 10 times 10. So what does this give us? This gives us 5 raised to power 4 over 10 raised to power 4. 5 in 4 places, 1, 2, okay? Let me make that simpler. This gives us 5 in 4 places, 1, 2, 3, 4, 1, 2, 3, 4. So this is 5 over 4. Sorry, 5 raised to power 4, 10 raised to power 4. So that's what 6 times 5 and 10,000 gives us. 5 raised to power 4, 10 raised to power 4. So we have 4 raised to power x is equal to 5 raised to power 4 over 10 raised to power 4, which is the same thing as 4 raised to power x is equal to 5 over 10 raised to power 4. Now, 5 over 10 is not yet in its lowest form. It can be further reduced. So we have 4 raised to power x is equal to 1 over 2 raised to power 4. Now, 4 raised to power x is equal to, we want to write 1 over 2 in index form, in indices, or how should I put it? As an indices, yeah. 1 over 2 as an indices. We have 2 raised to power minus 1. Negative indices, 2 raised to power minus 1 into 4. So this gives us 4 raised to power x is equal to 2 raised to power minus 1 times 4, which gives us 4 raised to power x is equal to 2 raised to power minus 4. Now, looking at our left-hand side and our right-hand side, there is no correlation between 4 raised to power x and 2 raised to power minus 4. So we cannot say we want to equate indices or do anything. So what do we do in this case? What do we do? Now, our left-hand side is not untouchable. Note that your left-hand side is not untouchable. So having 4 raised to power x, 4, which is our base here, can be further broken down. 4 is the same thing as 2 times 2. So we have 2 times 2 raised to power x. And 2 times 2 is the same thing as 2 raised to power 2 into brackets. And we have our power of x. So when we open this bracket, we have 2 raised to power 2 times x, which gives us 2 raised to power 2x. This is 4 raised to power x. We've broken that down. So we come back here. We have 4 raised to power x is equal to 2 raised to power minus 4. Is now 2 raised to power 2x is equal to 2 raised to power minus 4. Now we have equal bases. So we can talk about equating indices or equal bases. So we have 2 raised to power 2x is equal to 2 raised to power minus 4. 2 cancel 2. We have 2x is equal to minus 4. So you divide both sides by 2. So we have 2x over 2 is equal to minus 4 over 2. 2 cancel 2. We have x is equal to minus 2. This is our answer. So, then okay. This is example. This was example, I think 4. We have let log. Okay. We just have log square root of 128 is 2 root 2. Square root of 128, then 2 root 2 as our base. So we say let log square root of 128 base 2 root 2 is equal to x. So when we write this in index form, we have 2 root 2 raised to the power of, sorry, it's z, not x. Okay, we can use x. X is x. X is equal to square root of 128. Now, what do? We have 2 root 2, sorry, as our base, and we have square root of 128. Let's work on our right hand side. We have 2 root 2 to the power of x is equal to 128 raised to the power half. Note that. Now, can we break down 128? That should be possible. So, let's break it down to, we said it must have a relationship with a left hand side. So we're having 2 root 2 here. So let's say we'd have to deal with 2 here as base 2. So let's break this down. Or let's start from the left hand side. Let's make the left hand side a proper base so that we'll know what base we are breaking the right hand side down into. Now, if we want to work on 2 root 2 as a base, this is not a proper base because you cannot break down 128 into 2 root 2. So we have to make this a proper base. Now we have 2 root 2. 2 root 2 is the same thing as 2 times root 2. 2 times root 2 will give us 2 root 2. Now, root 2 is the same thing as 2 raised to power half. Don't forget I said square root in mathematics means power of half. So we have 2 times 2 raised to power half raised to the power of x. So now don't forget that 2 is the same thing as 2 raised to power 1. When you are working on indices, in fact, when you are working on mathematics generally, you must be able to think outside the box. So 2 is the same thing as 2 raised to power 1. So we have 2 raised to power 1 times 2 raised to power half into power of x. Now we apply the law of indices here to work with this, where our multiplication sign changes to addition of power. So we have 2 into 1 plus half raised to the power of x. When you add up 1 plus half, you have 3 over 2. So we have 2 raised to the power of 3 over 2 raised to the power of x. So when we open this bracket, we have 2 raised to the power 3 over 2 times x, which gives us 2 raised to the power 3x over 2. Now we worked on our left-hand side. This is now a proper base and power. So we come to the right-hand side. Coming to the right-hand side, we have square root of 1 to 8. So if we break down 128, saying it must have a relationship with this. 128 is the same thing as what? 2 raised to power whatever. So that should be, okay, we've said this is 128 raised to power half. Yeah. So we have 128 to be 2 raised to power 7. 128 is 2 in 7 places. And I write that now. 2 times 2 times 2 times 2. It's 2, 1, 2, 3, 4, 5, 6, 7. 2 times 2, 4. 4 times 2, 8. 8 times 2, 16. 16 times 2, 32. 32 times 2, 64. 64 times 2, 128. So this gives us 2 raised to power 7, the power of half. When we open this bracket, we have 2 raised to power 7 times half. This gives us 2 raised to power 7 over 2. So let's write out the equation in the proper sense. So now we have 2 root 2 raised to the power of x equal to square root 128. This has become 2 raised to the power of 3x over 2 equal to, and this has become 2 raised to the power of 7 over 2. When we equate indices, or equal bases, we have 2 raised to the power 3x over 2 is equal to 2 raised to the power 7 over 2. This cancels, so we have 3x over 2 is equal to 7 over 2. How do we solve this? We cross multiply. Note that when you are talking about writing exams like NECO, it is not just about what you know. There are students that are very good. They know what they are doing. But at the end of the day, when the results are, they are like, this is not what I'm expecting. In mathematics, or further mathematics, you have to explain your steps. For instance, now, you jump maybe like 2 steps, and then you just, because your marker, whoever is marking your script, the person is marking your script as though I don't know what this is about. If I'm to mark a script, like a student script, I'm marking it as if I don't know mathematics. So it's as if you are the one guiding me, you are teaching me, you are showing me step by step how you arrive at your answer. So it is not just about knowing what you are doing and you are jumping steps. Every step counts in mathematics. This might be half mark, this might be half mark, this might be half mark, half mark, half mark. When you add up all of these half mark in 10 places, for example, we give you 5 marks. Now, imagine you jump all of these steps and then you just arrive at this, and you're assuming that I should know it. As a person marking a script, I don't know it. You are teaching me. So you should write out every step by step, how you arrive at the answer, not just jumping a step. Those steps you are jumping carry mark. And when in a whole question, you've jumped maybe 10 steps, that's 5 marks. 5 marks means something. In one question, you jump 10 steps, that's 5 marks. If in your theory, you have to answer maybe 4 or 6, and then you jump 5 marks, 10 steps, 5 marks in 4 or 6%, that's like 20 to 30 marks. So every step counts. And you see all of this, cross multiply, divide both sides by 2. All of these things I'm writing, they carry mark. So don't just ignore it and be like, they should know. No. In all your rushings, in all your, I want to be fast, I want to quickly finish whatever question, I want to manage my time effectively. Don't jump all of these steps. Show every step. Even your workings, you can show it on one side just to make them know you know what you are doing. You did not copy. You know how you arrived at your answer. So that is that for that. So when we cross multiply, we have 3x over 2 is equal to 7 over 2. When we cross multiply, we have 3x times 2 is equal to 7 times 2. So 3x times 2 gives us 6x. 7 times 2 gives us 14. So we have 6x is equal to 14. We divide both sides by 6. Divide both sides by 6. You have 6x over 6 is equal to 14 over 6. So we have our 6 cancel 6. And then we have x is equal to 14 over 6. When we reduce this to its lowest term, that should be 7 over 3. Divide both sides. We have 14 over 6 divided by 2 divided by 2. So you have 7 over 3, which is 2 number 1 over 3. So that is our answer, 2 number 1 over 3. So I will move on to the laws of logarithm. Okay. Laws of logarithm. So the first law, we have the product rule. Just as in indices, we have multiplication rule, division rule, negative indices, and all of that. So also in laws of logarithm, we have the first one is the product rule. So when you are given log mn, product multiplication, log mn base a multiplication, mn is the same thing as m times n. You have it as log m base a plus log n base a, as much as the base are the same. So mn is the same thing as we said product m times n. The second rule is the quotient rule. If we have log m over n base a, it's the same thing as log m base a minus log n base a. Let's do with examples relating to this. There are other rules. Okay, maybe I should just list out all of the rules. First off, the third rule, we have our power rule. So we have when you say log n raised to power n base a, that is our number itself or our logarithm itself has a power. It is the same thing as the power it is carrying comes behind, becomes n log m base a. The fourth rule, logarithms to its own base. And when you have the logarithm of a number to its own base, it is always 1. That is your base and logarithm, when they are the same, it is always 1. So for instance, you have log 100 base 100, it is 1. The logarithm to its own base, and the logarithm and the base are equal, it is always 1. The fifth one, power of the base so you have logarithm of x base b raised to power 3 when our power has a base. Sorry, when our base has a power of the base. Our base b. Here now we have logarithm of x base b has a power of 3. So when you have power of the base, your base has a power. So it is equal to 1 over 3 log x base b. Don't forget that the third rule, when we talk about power rule, that is when the logarithm itself is carrying a power here. The power comes behind as a whole number, an ordinary number. But look at the power of the base. When the power is on the base, not on the logarithm itself, it is a reciprocal number. That is, the power here is 3. So instead of the usual rule, when it is on top the logarithm coming as a whole number, it is coming as a reciprocal of the power 3 in our power. It's coming as a reciprocal of 3, which is 1 over 3. 1 over 3 logarithm of x base b. Then the sixth one, inverse rule. A logarithm of m base a is equal to m. Now we call this inverse rule. Inverse in the sense that our base and then the number before the base is the same thing as, is the same. And then your logarithm and the answer is the same. What are we trying to say now? Representing this in using the power rule formula. This is the same thing as saying, the logarithm of m raised to power a base a is equal to m. And look at your rule 3. It comes here. So this is just like we have this whole number. So it is the same thing as the power of the logarithm. So this is the same thing. Now we call it the inverse rule because the base and the power of the logarithm are the same. And the logarithm itself and its answer are the same. So just like mirror, how should we put it? Mirror numbers. This and this are the same, this and this are the same. So it is called the inverse rule. The seventh one. So we have reciprocal law. So when we have logarithm of a base b is equal to 1 over logarithm of b base, logarithm of b base a. When the reciprocal of a logarithm is required, the base and the number interchange their position. When the reciprocal of a logarithm is required, the base and the number, they do what? They interchange their position. So if we have logarithm of a base b, the reciprocal will be 1 over logarithm of b base a. This and this change position. That is what the reciprocal law or rule is about.
Can you hear me? You have about,
Yes.
you have less than 10 minutes to go.
Less than 10 minutes, okay. Change your base. change of base. So when we have logarithm of x base a is equal to logarithm of x base a over logarithm of a base a. Don't forget that logarithm of a base a is the same thing as 1. So we have logarithm of x base a. This is the same thing as 1. So this is just the rule. This is the rule. This is just an explanation. So we have the 9th rule, logarithm of 1. We have logarithm of 1 base x is equal to 0. The logarithm of 1 to any base be 1 million is what? 0. The logarithm of 1 to any base is 0. We come to the 10th rule, which is our final rule. Logarithm of 0. So the logarithm of 0 to any base is undefined. I don't know if you've read anything called undefined before. This is undefined. So the logarithm of 0 to any base, logarithm of 0 to any base is undefined. Undefined means there is no answer to it. So I have some assignments for practice. First question. Express log 0.04 base 5 is equals to -2 in index form. Question 2. Express 64 is equals to 60 raised to power 3 over 2 in logarithmic form. Question 3. Evaluate 1 log 1.78 base 1.2, and then 2 log 0.2 base 625. So I'll be all for today. Next class we continue with laws of logarithm. Thank you. If you have any questions, you can maybe drop it with Miss Jason or at the comment section. So that will be all. Thank you.